Welcome to Comfy Cozy Chapter 2 Applications with Jason Barnett, your host. We have pictures today. Look, I'm like a weather reporter. Wait, I'm like a weather reporter. Yeah. So, Chapter 2 is all about what are some of the things that we can do with integrals. We spent Chapter 1 talking about how do we do it. Chapter 2 is what can we do with it. And then Chapter 3 is just going back to Chapter 1 and saying, let's do some more complicated integrals. How do we do more fancier integrals? So we have here a picture of Hoover Dam. Extra credit points, but not really. If you appreciation points, if you knew that this was Hoover Dam. And dams are great in applications of integrals. Because if you think of all the pressure that the water is exerting on the dam, the lower you go, the more pressure. And, the bigger the area, the more pressure as well. And so we'll be talking about that in section 2.5, how to calculate those forces. And so a lot of calculus goes into building something like this. Something else that's cool with integrals is if anyone's seen this little trick here, and you were curious as to how it worked, integrals have the answer. We may or may not have time to get to this section. But yeah, you can think of these. It's really all about the center of mass. Notice that all the weight, right, is on the toothpick right here. So if the center of mass is above that, it tips this way. If the center of mass is over here, it tips this way. If the center of mass is to the left, it'll tip that way. So the fact that it balances actually tells us that the center of mass is right here. And the center of mass is also an integral. If the mass is equal density, then it's a single integral. If the mass has variable density, like this one does, and depends on if we're looking at 2 dimensions or 3 dimensions, if it has variable density, then it has more integrals, which is something that you could do in multivariable calculus, which at SPSCC is Calc 4. Okay, so loads of cool stuff, applications of integrals, and that's what we're here for. But we're going to start with something a little simpler than those things. We're going to start talking about the area of a region between curves. Now you might say, Jason, we've already done this. I hope so. I hope you're saying that. In which case, smooth sailing. But in the event that you don't remember, quick review, and we'll show what's different, what's the same. Let's say I have some function, and I'm curious about the area from A to B, the area under this curve. Well, we know that we can graph this area like this. We can approximate it with a bunch of rectangles. And we said, well, the area under that curve is just the integral of that function. If this is a rate of change, the area represents the net change of the other quantity. So if this is velocity, area represents the displacement, the net change of the position. Well, what we're going to do in this next section is something very similar, but now what if there's not just one curve? What if there's 2 curves? What if we have a function f of x and a function, hold on, let me make this graph, g of x? Well, what if we're looking at this blue region? Well, the geometrically inclined people might recognize something that we can do. What is this blue region if not the red region minus the yellow region? Wait, hold on, we should go in. Right? Blue is just red minus yellow. Don't mention that in an art class. They'll probably, I could actually use colors that made sense. I could have been like blue is like green minus yellow or something like that. But I didn't. In this case, blue is just red minus yellow. And that's how we'll set things up. So this first one is just the integral from a to b of some function. And the second one is just the integral from a to b of f minus the integral of g. And we subtract integrals, we can combine their integrands and write this as just f of x minus g of x. Like so. because really this is just two integrals subtracting, and they have the same limits of integration. So that's what we're doing in this section. So we can introduce this as a theorem. Theorem 2.1 is what the book calls it. You know, let's include the numbers this time. Everyone loves some numbers. Let f of x be greater than or equal to g of x. That's important. On some interval a to b. Doesn't have to be true for everywhere, but just from a to b. Then the area, this is just restating what we already said, between f and g is, well, on the area, sorry, that area between f and g on the interval, let's be precise, is just what I wrote down on the previous page. But this is the more formal version of what we introduced graphically at the start of this video. We got this nice theorem for areas between curves. And again, this is important. And it's probably not important in the way that you think it's important, but we'll do some exploration in this section. We're going to see and have some motivating examples and see why we need certain things and what happens if we don't have them. And can we fix those problems as they come up? So let's get into an example. Example 1. Find the area enclosed by the curves, and then we'll have multiple parts. Part A is just going to be the curve f of x equals x plus 4. That's just the equation of a line. And g of x equals 3 minus x over 2 on the interval from 1 to 4. So how can we find the area between these functions on that interval? Well, most of the time, it's a good idea to have a graphical image of what's happening. So let's do that. Let's get a graph. This one is easy enough to be graphed by hand, so let's graph it by hand. We have two lines. We're looking at the region from 1 to 4. The first line is x plus 4. All right. I should have looked at that before I drew this picture. The first one is x plus 4, so we're going to need to be a little higher than this. So y-intercept of 4. And then slope of 1. All right, I didn't give us quite enough room. And the second one, let's color code this. The second one is 3 minus x over 2. The y-intercept of 3 and slope of negative 1/2. Should look like this. And we're looking at the region from 1 to 4. Starting here, 2, 3, 4. Up to here, specifically, we are looking at this yellow region. All right. How can we find the area of this yellow region? Well, I'm hoping, one of my students had this great analogy of, you know, calculus is a car, but he's getting everywhere around by donkeys, which is like other problem solving. Well, there's a donkey method of solving this problem. And that's that you could just find the area of the parallelogram. Right? This yellow area is just the area of a parallelogram, just the average of the bases times the height. Okay? That's the donkey method. You don't have to ride in a car and use the gasoline, pay for the car, you just ride your donkey. Get there the same way. Well, let's practice driving a car. Okay? Let's practice driving a car and use some calculus. So if we do that, then what we can do is we can say, I'm going to use the big one because I don't want my marker to look like the graph. We know this area is going to be the integral. Whoa, that's not an A. We know this area will be the integral from A to B, in this case 1 to 4, the x coordinates denoting this, of the top function minus the bottom function. Well, the top function is f. That'll be x plus 4, minus the bottom function, 3 minus x over 2. And I've made a mistake. Besides besides writing off of the screen. What mistake did I make? Top function minus bottom function. The mistake I made is I didn't distribute that negative. We're subtracting this whole bottom function. So it's the negative goes to the 3 and the negative goes to the x over 2. The negative x over 2 and those negatives cancel. So when you're subtracting, make sure to subtract the whole thing. Now we can simplify and then take the integral. Integral from 1 to 4. This becomes 4 minus 3 is just 1. X plus x over 2 is 3x over 2. All right, and then we can take the antiderivative. That'll be x plus x squared divided by 2 from 1 to 4. And just plug in 4 and plug in 1. And subtract. And when you do that, you should get 4 plus 12 minus 7/4, I think. 6. Doing too much fractions in my head is bad, but here we are. 16 minus 7/4. 16 is 64/4 minus 7/4. So 57 over 4 is our answer. Let's check our answer with parallelograms. All right, so this height over here is 2.5. Parallelogram is 1/2. Then the sum of the bases, so 2.5, I'll write as 5/2. Plus the other base is 1, 2, 3, 4, 5, 6, 7. 7, I think. Times the height, which in this case, the height is horizontal, and that's 3. So if you do that, that becomes 19 halves times 3 halves. Please tell me that's 57 over 4. It's 57 over 4. That's fantastic. Great. So the donkey method, same as the car method here. So the question is, and again, we could check this with GeoGebra, Desmos. The question is, what happens if you get the order wrong, right? If you just choose the wrong function to be on top. Well, that would give you the integral from 1 to 4 of 3 minus x over 2 minus x plus 4. If you got the order wrong, what do you get? You just get the negative answer, right? Because if you get the order wrong, look at the formula. If you get the order wrong, that just changes the order. That's just the negative version. So yes, we need the f to be bigger than g, but if we choose the wrong top function, we're just going to get a negative answer and we can just flip it. All right, no big deal on that one. So something to watch out for. You do choose the wrong function to be on top. It could work out mostly. We'll see in a future video what can also happen. But yeah, if you get a negative answer for this area between curves, remember area is always positive, but integrals represent net signed area. So watch out for that. That's everything for this video. The next one has more examples. Good luck. Get some more practice. The next one's got some fun ones. And yeah. Enjoy. Bye-bye.